is. So let me just turn on the laser pointer. So I have many collaborators, that have helped me with the work that I'm presenting today, but specifically the topic of this presentation is with my recently graduated PhD student, Brandon Zimmerman. And so I wanted to, acknowledge him here. I'm gonna just, sorry, I need to, apparently if I have the laser pointer, I cannot. Okay, sorry, don't worry about it. I was trying to arrange my Zoom settings. So, continuum thermodynamics. So the topic of my presentation today is continuum thermodynamics, not the kind of thermodynamics that we learn in our undergraduate engineering, education. It's the kind of, thermodynamics that was motivated by the continuum formulation of the second law of thermodynamics, the axiom of entropy inequality, by Clifford Truesdell and Richard Dupin. So you may be familiar with this, you may not be familiar. If you're not familiar with it, I'm going to cover most of the background in this presentation, so you should hear every aspect of it. The other thing that I want to say is that, we're going to be, the main role of the second law of thermodynamics is to constrain functions of state. Functions of state include, for example, the stress in a material. And there are two methods to analyze, continua. One is using only observable state variables. And I will explain what are observable state variables in a moment, but think of it like strain. You can measure the strain in a material. But there are many processes in mechanics that require the hypothetical introduction of internal or hidden variables, like a dashpot in a viscoelastic material. There's no actual dashpot in the material, but you imagine one conceptually, and that becomes an internal variable. The framework for both observable variables and internal variables, the thermodynamic framework, was presented by Coleman, with Knoll in one case and with Gerton in the other. So therefore, dissipative mechanisms in solids often are described using internal variables. Viscoelasticity is an example, so the viscous dashpot is an internal variable. Damage mechanics, the amount of damage becomes an internal variable. Plasticity would be the plastic deformation becomes an internal variable. And interestingly enough, growth mechanics, the deformation due to growth becomes an internal variable. The total deformation is what you measure, but you assume some of it is due to the growth. So in order to understand what are the functions of state that we encounter, we have to look at the axioms of conservation. Again, this should be familiar to all of you who do solid mechanics, but I'm going to present it assuming that at least to introduce the notation. So what we have is the axiom of mass balance, where rho is the mass density, v is the velocity of the continuum, and the dot operator is the material time derivative. The axiom of linear momentum balance is the density times the acceleration is the divergence of the stress, that's the Cauchy stress, plus the body forces. This is the body force per mass, or the specific body force. The axiom of angular momentum balance for nonpolar media says that the stress is symmetric. The axiom of energy balance, which is also known as the first law of thermodynamics, is given in this form. And let me spend a little extra time here. So epsilon is the specific internal energy, so internal energy per mass. Q is the heat flux, it's a vector. R is an important variable. It's an internal source of specific heat supply. So it's an internal source of heat generation for phenomena that you haven't modeled explicitly. So if you pass a current through a resistor and there's Joule heating, then you actually can say, oh, the Joule heating is due to this internal source. But you could also formulate a problem where you allow charged species to flow relative to static, charged species and create friction between them. So R is really a placeholder for phenomena that you choose not to model explicitly. This is something that I'm kind of presenting in a way that is not the standard way. I want to emphasize this. R could be also the source of heat generated by reactions. L here is the velocity gradient. It's the standard notation. Okay, so these are the axioms of conservation. So those are the general axioms. In these axioms, these equations are not sufficient to solve for all the unknowns that appear. So what we have are functions of state, the stress, the internal energy, the heat flux. which we need to provide constitutive relations for these functions of state in order to solve this complete set of equations. Otherwise, there are not enough equations. And these equations of state represent the behavior of specific materials. Do you want to model a fluid? Do you want to model a solid? Do you want your solid to be elastic or viscoelastic? Do you want it to be thermoelastic, etc.? You make the choice. You, the modeler, you decide what are the models you want to assign. And then the only thing that remains is, what does the second law allow you to do with these equations that you proposed? You know, it places constraints on them. So how do we apply those constraints? So here, let's understand the Clausius-DM inequality, the entropy inequality. I'm not going to explain the concept of entropy, you know, in great detail. I assume you all have some conceptual understanding of entropy, but basically, the second law says the following. So heat flux divided by temperature, we call this the thermal entropy flux. So if heat is flowing and you divide that by the temperature, that entropy that it brings with it is due to the heat flux. We call it the thermal entropy flux. If the thermal entropy flux diverges, or rather if it converges, it will increase the entropy, right? The time rate of change of the entropy will be positive. Similarly, if you have entropy generation from the heat supply, then it will also increase the entropy in your system. But the second law says that these two sources are not enough. There will be greater entropy generation than the entropy that's carried by the entropy flux and by the internal source of entropy generation. Okay, so that's what the second law says. So now what we ask ourselves is, well, a moment ago I explained to you this R is not a, you know, defined quantity unless you decide, oh, I want specifically, you know, Joule heating or microwave radiation, microwave heating. So we should try to eliminate R from the entropy inequality. So what we do is we go back to the energy balance and we write it in a form where we bring all the terms to the left-hand side. And we say, oh, look, there's a rho R here, there's a rho R here. So all I have to do is take the entropy inequality and multiply it by theta and expand this divergence operator. Then if I take the sum of these two relations, this div q cancels out with that and with this, and you end up with the alternative form of the Clausius-DM inequality, where you introduced a new function of state, which is usually called the specific free energy. The specific free energy is usually named after Helmholtz. So, but I'm not going to use the names of scientists because I prefer descriptions which are straightforward. Free energy. What does free energy represent? It represents that part of the internal energy which is available for useful work. So if you think of strain energy, for example, if you take a spring and you compress it, what you've done is you've stored strain energy in it. This becomes a free energy source. It's available for use for work. If you let go of the spring, you're going to recover. But that's not the only source. Strain energy is not the only source of free energy. You can also have a thermal source. Consider that you have a gas in a piston cylinder assembly. You compress the gas. So now it's like a spring, but you add heat. When you add heat, the pressure in the gas is going to increase. And now when you let go of the piston, you can generate work that was, you know, produced by the heat that you added. So there's a thermal component to the free energy as well. And then the random part of the vibrational motion of the molecules is associated with the entropy. Okay, so as long as we understand these basic concepts, we should be able to understand how this works. So how do we apply the entropy inequality to place constraints on the constitutive models for our materials? That was, in fact, the work of Coleman and Knoll. So all of this, for many of you, it's history. It's a long time ago. But you have to remember that thermodynamics, which is taught to you in your undergraduate textbooks, is the thermodynamics developed in the 19th century. This here is the thermodynamics of the 20th century, which is not widespread. It is taught only in graduate level courses and not always in the same way. There are no standard textbooks that explain it really well, in my opinion. This is just me. I'm an opinionated person when it comes to these things. Anyway, Coleman and Knoll did this amazing thing. They said, this is how you should apply the second law to place constraints. What you do is, this is the Clausius-DM inequality. We saw a moment ago what we had. Now you decide what kind of material do you want to model. So for example, for an elastic material, what you want to do is you want to select which are the state variables that matter to you. So for an elastic material, you say, well, I expect that the stress should depend on the strain. So you add the deformation gradient, from which you can derive various forms of the strain. And if you want your material properties to depend on temperature, you can add temperature. And that's it. It's a modeling choice you made. You restricted your choice of state variables to temperature and deformation gradient. These are observable, state variables. You can measure temperature, you can measure deformation. Then what you do is, you notice that in this Clausius theorem inequality, the only function of state which has a material time derivative is the free energy. So you apply the chain rule based on the dependencies that you chose. You chose a dependency on temperature and deformation gradient. You apply the chain rule, you make use of a kinematic identity, which you probably learn in your graduate course, and you substitute this back in here, and then you group the terms together. So now you've substituted the material time, the chain rule, based on your choice of state variables, and you've grouped terms together. Now comes the part where we use, the arbitrariness of processes. We ask ourselves, if I want the second law to be valid for arbitrary processes, that means arbitrary variations in state variables. So the temperature, the rate of change of temperature is arbitrary, the velocity gradient is arbitrary, the gradient of temperature is arbitrary. And you treat the gradient of temperature as a separate quantity than the temperature, because the temperature is a scalar, the gradient of the temperature is a vector. So you could have the temperature here has a certain value, but the gradient is a vector. It can be oriented differently. So you treat it as an independent variable. How could this inequality be valid for arbitrary variations in theta dot, in L, and the gradient of theta? So the answer is, let's look at this first term. This term here in the parenthesis does not depend on theta dot. So if theta dot is positive or theta dot is negative, there's no way to guarantee that this term will be positive unless this term is equal to 0. You see, that's the only way you can satisfy the second law. So then you say that the entropy is the negative of partial FC, partial theta. The same applies here. We decided that the free energy doesn't depend on L. This was an a priori assumption that we made, in which case this term must be 0 because the components of L could be positive, could be negative. And we have no dependence on the gradient of temperature, so how could that be true? That means that the heat flux should be 0. So if you choose an isothermal context, then the heat flux must be 0. The entropy is given by the negative of the rate of change of free energy with temperature, and the stress is given by what is usually called the hyperelasticity relation. You see? So this is how we do, and then when you substitute these expressions here, you see that you end up with 0 is greater than or equal to 0. That means there's no residual dissipation. There's no dissipative mechanism. Elastic materials, are idealized materials. They give you reversible processes. In thermodynamics, all the energy that you put in the spring is recovered when you unload the spring, if you assume these ideal conditions. Okay. Now what happens with the concept of internal state variables? So this again was introduced in 1967. Let's say that you want a viscoelastic material. So you have a spring in series with a dashpot. So the spring and dashpot, you can measure the total deformation. So the deformation gradient is an observable variable. You can measure the whole deformation. But the dashpot deformation is an internal variable. So you introduce an internal variable. Here I called it A because this is not limited to the dashpot. I'm just illustrating internal variable theory using the dashpot, spring dashpot. So what you do is you say, okay, so I would like to figure out the deformation of the dashpot because I know that the velocity of the dashpot will give me a force. So then what happens is, because you added an internal state variable, which you cannot observe, you can only measure the total deformation, you have to make some assumption about the deformation of the dashpot, then the chain rule means that you have an additional term, which is this term here. And then when you plug everything back into the entropy inequality, everything else looks the same, but you have this additional term, which has a dot. What is a dot? If it happens to be the dashpot deformation, then maybe it's the velocity of the dashpot. So now what you need to do is, because you created this dashpot from your imagination, it's an abstract concept, you need to propose a constitutive relation for how the rate of change, the time rate of change of the dashpot, or the internal variable A depends on the other state variables. So you need to propose an evolution equation, which is great. And then you have to impose the additional condition that this evolution equation should satisfy this inequality, which means, you know, maybe you need to propose a dependence of psi on A explicitly, although in viscoelasticity, rarely do you see an explicit relation. You just need to satisfy these inequalities, and then the rest of the relations remain the same. So this is internal state variable theory. It's very powerful. It has worked really well. What I'm going to propose is that that's not the only way that we can do continuum mechanics. So the thesis that we are putting forward, my student and I, my former student Brendan and I, is that we can actually describe the broad field of continuum mechanics using only observable state variables. So observable state variables, which I promised you a definition, are all based on measurements of time and space, because that's the world we live in. And remember, I'm talking about Newtonian physics here. I'm not talking about Einsteinian relativity theory. So length, area, and volume and time are the things that we can measure. And force is then measured usually using a calibrated material whose deformation you can measure. And you say, aha, the force is related to that deformation. Mass is then calculated as you divide force by acceleration. And temperature, you know, thermometers, you look at the change in length of a column of mercury. So once again, temperature is a derived measurement. Or you could say the wavelength of, you know, infrared radiation from a, you know, heated body. Whatever it is, you can actually say that all of your fundamental, you know, variables are derived from length and time. So to include the wide range of dissipative processes that we find in here, I propose that we should use mixture theory. We have to allow that there's multiple constituents in our continuum. And so the common functions of state in a mixture will continue to include stress, heat flux, internal energy, and entropy. But here's where we differ. If you have a reaction in a mixture, you have reactants and you have products. When these products are created, they're created at a time, let's say at the current time now, which is, you know, later than the time of your reference configuration, which means that any product created at the current time needs to have its own reference configuration associated with it. You cannot simply say, oh, the reference configuration that existed at an earlier time should apply to the material that came into existence now. So that means that you really need to include the reference configuration of your products of the reaction as a constitutive model. And that's a pretty, you know, major deviation of conventional way to do continuum mechanics. And I'm going to explain this concept in greater detail. So I'm going to skip now to the next slide and try to explain to you what was the motivation for this. Basically, it was our experiments in growth mechanics. So there are two traditional schools of thought in growth mechanics. One is that growth represents the addition of mass to the solid matrix of your material, right? So you could say a mountain grows because, you know, lava, which is a liquid, solidifies, turns into a solid. We call this appositional growth, right? Doesn't have to be biological, but you could also say, oh, I have a filter and I have a solution that's flowing through it, and some of the filtrate gets stuck in the filter, so now the mass of the filter increases, right? So you actually increase the mass of the filter because there were, you know, solutes that were in the solution that got trapped in it. So growth mechanics does not have to be biological. It's important to understand. But the people who actually proposed the concepts of growth mechanics are in the field of tissue mechanics. So in this case, when you convert solute mass to solid, what you have is you increase the mass of the solid. That's an observable state variable, which is very nice. But Richard Scalak, who's a professor at Columbia, he's now passed away. He went to UCSD, but I took a class with him back in 1986 or 87. So Richard Scalak proposed that actually growth should be a kinematic quantity. Like I explained earlier, you explained that growth is like a change in shape. But he didn't write down a set of equations. That was done by Ann Hoger and Andrew McCullough with their student, you know, Rodriguez in 1994. I'm sorry, this is a mistake. It's in 1994. Basically, they took the deformation gradient and they split it into an elastic part and a growth part. They said, if you see this much change in shape, some of it is due to the deformation, some of it is due to growth. This split introduces an internal variable, which they call the growth tensor. So I don't adhere to that approach for the following reason, because I've done my own studies of growth mechanics experimentally. So my interest has been in cartilage. My funding comes from the National Institutes of Health, and I've been interested in understanding cartilage degeneration. So this is your humerus, okay, the humeral head, the ball and socket joint of your shoulder. And this is this white glistening surface that you see is articular cartilage. It's about 2 millimeters thick. With arthritis, it wears down, and here you see bone underneath it. And the cartilage itself in adults is not innervated, so you don't feel pain in the cartilage. It's the bone that has nerves in it. That's what causes the pain in arthritis. So starting in the 1980s, people before me decided, hey, maybe we can grow cartilage in the laboratory, maybe to fill these types of defects in the tissue. So the field of tissue engineering came into existence in the 1980s. My colleague Clark Hung and I started working on it in 2000, and Rob Mock was our shared graduate student at the time. Basically, what we have here are agarose discs that have been seeded with bovine chondrocytes. So these chondrocytes are the cartilage cells. We obtain them by going to the slaughterhouse in the morning when the cows have been slaughtered, and we bring the joints back to the lab, we isolate the cells, and we put them in these constructs. What we found is that on day 0, the construct has, looks like this, and on day 42, the size hasn't changed much, but you clearly can see that something grew inside. So the mass of the construct has changed, but the volume hasn't changed, so it's not a kinematic growth. When you actually do histology, you can stain for the cells, which appear in red, and this little cloud that you see around it is the collagen matrix that was formed by the cells. In the beginning, the collagen comes out from the cell, deposits in the neighborhood, but over time, it fills all the space. And then, microscopically, the collagen is too small to see under a microscope, but, you can see this opaqueness here. And just as okay, good. Now you can measure, there are biochemical assays that let you measure the composition over time. So this here is the collagen content as a % of the wet weight. You weigh the construct and you dry it out, then you measure the collagen content. You can take it as a, wet weight, or you can convert it into mass per volume. You see, over days in culture, it increases. So you can track the composition of your material over time. Obviously, as the composition of collagen increases, the construct becomes stiffer. I'm not showing you the material properties, but you also have that the material properties depend on the composition. Everything varies with the composition. These are different culture conditions. They all show an increase in collagen. So basically, you can measure the compositional changes. There's no appreciable shape change. This type of growth cannot be described by the growth tensor. So fundamentally, I don't think that the growth tensor is the right way to describe growth mechanics, certainly not in this case. So you only need one exception to invalidate the theory, you understand? And this is a pretty important exception. So what is interstitial growth? Basically, let's assume that you have your, cell-seeded construct, and, the blue region represents the porous domain that contains some kind of matrix. This could be the agarose or some initial generation of collagen. Then the cells produce more collagen fibrils. So you have interstitial, like the pore space becomes denser. You reduce the amount of, fluid, and you substitute it with solid. And what Cowan and Higgius proposed in 1976 is that you can describe this by change in the apparent density. The apparent density, by definition, is the mass of one constituent divided by the volume of the mixture. So in this case, the reaction is that cells, which are our factories, take solutes, such as proteins, and convert them into solids, such as collagen fibrils. So in mixture theory, we use apparent quantities. So you divide the content of each constituent by the mixture volume. So that means that interstitial growth can be modeled using reactive mixtures. So what is mixture theory? I'm throwing out a bunch of references for you here on the screen, just so that you're aware. But the work was, again, the work of Truesdell. This paper in 1957 was written in Italian journal, so I was never able to find it. If one of you can find it, send it to me, I would be grateful. I would still have to translate it, but really I've been looking at the work of Truesdell and Tupin and all these other people who focused on reactive mixtures. But applications of mixtures, not always reactive to biological tissues, started fairly early on. If you think that really mixtures were developed in the 60s, by the 70s, several people were using this. Van Ma was my advisor, Michael Lai was my advisor, so that's how I became familiar with mixture theory. Anyway, now you know that when you compress a material, the density changes. So a change in density is not uniquely associated with growth. It could be associated with deformation. So how can we separate growth from deformation? The answer is, this is your mixture in the reference configuration. We call this elemental volume dVr. And what you have is, this is the mixture in the current configuration, and this is the mass of the solid in the current configuration and the volume in the current configuration. So instead of dividing the mass in the current configuration by the volume in the current configuration, you can divide it by the volume of the reference configuration. So you end up with a quantity called the referential mass density. But since the mass of the solid could change as a function of time, but the volume in the reference configuration doesn't change, then rho RS only tracks the growth. So you can relate it to rho S using the ratio of the volume in the current configuration to the volume in the reference configuration. This is a standard procedure in solid mechanics. You take the mass balance equation, but in our case now we have a mass supply term. This is the amount of mass that's added to the solid due to reactions that involve the solutes. The fact that the cell is the factory is not relevant here. This is a continuum mechanics representation. So then you substitute the kinematic relation that Js, which is the determinant of the deformation gradient, is related to the velocity through this relation. Material time derivative of Js is Js times divergence of Vs. Substitute that in here, integrate this equation. You end up with an integrated form of the mass balance, or a referential form, which says that the time rate of change of the referential mass density is governed by this mass supply term, which is a function of state. And this relation dates back to the days of Bowen and Weiss. I didn't come up with this, but somehow Bowen, who did a lot of reactive mixtures, didn't use his relation again later, which I find surprising, but I'm using it extensively. Okay, let me skip through. So obviously, if this term is 0, then there's no growth. That means rho RS doesn't change. So rho RS dot would be 0. Okay, so this becomes the evolution equation for composition. Remember, internal variable theories require evolution equations, but you have to formulate them as an abstract concept. They're not based on any fundamental axiom of conservation. What I'm saying is composition is governed by the axiom of mass balance, but there's a function of state when you accept that there are reactions. You have to remember, these are all critical points in this formulation. So that means that composition is a state variable. Whenever it changes, you have to add it as a state variable in your constitutive model. Now let me show you how we do this with mixtures. This is my former student, Bob Nims, who did this modeling while also running experiments on cartilage constructs. This here is an axisymmetric model of a disk, just like the disks that I showed you earlier. This is a very complex model. It's done computationally in a finite element code that I co-developed with Jeff Weiss called FEBio. Let me explain to you a little bit, because this one doesn't use constrained mixtures. This is the full-fledged mixture theory. It includes transport, it includes growth, it includes osmotic forces, and so on. I have a scaffold in which I have my cells. This scaffold consists of agarose. It's part of the porous solid. I modeled it with an Hookean material. Then I need to recognize that among the molecules that the cells make are these proteoglycans, which are made up mostly of chondroitin sulfate. Chondroitin sulfate is a charged molecule, and it binds to the solid matrix. So we model it as a solid-bound molecule. But there's a fluid inside, there's a fluid in the bath. The fluid contains water. It contains glucose as a nutrient that the cells need to make the matrix. It also contains sodium chloride, magnesium, and sulfate. Sodium chloride, because that's what our biological fluids contain. Magnesium and sulfate, because I want to convert the sulfate to chondroitin sulfate in a reaction that produces proteoglycans. So the reactions, there are two reactions. One is that glucose is consumed by the cells just to survive. So some of the glucose is only used to maintain the cells alive, and some of the glucose is used to convert the magnesium sulfate into chondroitin sulfate. So this model looks very simple, but you have to understand that there are cells in here which are not modeled explicitly, but all these constituents are in the model. We're only going to look at one thing. I don't have time to show you the whole set of slides. The chondroitin sulfate have a fixed charge density associated with them. The fixed charge density means there are charges that are going to grow here that are going to be deposited by the cells. And as a result, there's going to be an imbalance of charge inside and outside that's going to draw cations by transport from the bath. The cations include, for example, the sodium and the magnesium. The cations will enter at a greater concentration than the anions, such as chloride and sulfate, because there's already a negatively charged matrix in here. This will cause an osmotic imbalance, the difference in osmolarity between inside and outside, and that's going to cause an osmotic pressure. That osmotic pressure is going to swell the tissue, okay? So let's play the movie. So this is all happening. There's a little bit of osmotic shrinking in the beginning. The color is the chondroitin sulfate charge density. And so what you see is the swelling pressure is causing the shape change, okay? The swelling pressure is causing the shape change. The concentration of chondroitin sulfate is closer near the boundaries. Why? As glucose transports in, the cells which are closer to the boundary have greater access to glucose and to convert it to chondroitin sulfate. The cells deep inside the construct have less glucose, so they produce less matrix. So you get this inhomogeneous growth shape. But the growth was driven by the mass deposition, the deposition of chondroitin sulfate, and it's only the osmotic effects that were the consequence of the charge difference that caused the growth. Now, this is something that looks similar. So what you see here is the agarose construct shown in the same kind of axisymmetric cross-section, and the actual tissue construct that grew in a very similar shape. This is a top view. If you actually look at the final shape, you see it's caved in at the center, just like it shows here, which is very interesting. This is a study that made us realize that we need more access to nutrients deep inside. So we added channels in this study, but then the channels were blocked by the dish. So in subsequent studies, we had to stand the tissue constructs vertically to allow fluid to flow, but that's a completely different talk. That's not a thermodynamics talk. Anyway, that's a growth mechanics using mixture theory, but unconstrained mixtures. There's transport, there's solutes, and there's solid. But now I'm going to describe only mixtures that contain solids because they're less difficult to analyze in equations, even though this is already a complex presentation. So you have matrix that exists already at some initial time in your reference configuration, and it gets deformed. Here I showed compression in this slide, but in the previous slide you saw that the construct actually grew in size, so the volume increased. So it doesn't matter, but at some subsequent time, remember it took 56 days to grow these constructs. So at week 1 or week 2 or week 3, you can think of new generation of solid matrix that's deposited. This solid matrix didn't exist on day 0. So obviously it needs to have its own reference configuration at the time when it was deposited at time t alpha. And that is the concept that was presented in the literature, specifically by Humphrey and Rajagopal in 2002. They said you could have multiple solid bodies that can be intermingled like this. Then J. Humphrey's former student, Rudy Gleason, with his student Juan, actually specifically said each body has its own distinct and invariant reference configuration. He said that. And right about the same time, with Tim Ricken in Germany and I, Tim was a visiting professor in my lab, we actually formulated this multi-generation growth model where we also proposed the same thing, but we explicitly said that we need a constitutive model for each generation's reference configuration. Okay, so let's take a closer look at this formulation. Intermingled bodies, which are all solid constituents. Once the new collagen matrix grows into the existing collagen matrix, they move together. They're not, there's no constant separate motion. So they're not an unconstrained mixture. They're constrained to move together. So generation alpha has a motion which matches the motion of the master generation in the at the current time, even though they have different reference configurations. So that means that you can define a deformation gradient for each generation using the usual definition of the deformation gradient in continuum mechanics. But then you have to say, well, if they're moving together, that means the this reference configuration is not independent. There's no independence. In fact, what you're saying is using the chain rule, the master reference configuration, which is given by this definition, since chi s is equal to chi alpha at all times, then you can do the chain rule like this. You end up with the deformation gradient relative to the reference configuration of alpha times this mapping, which is time invariant, right? It's a mapping that says what's the difference, what's the relation between the reference configuration of generation alpha and the reference configuration of generation S. That partial of x alpha, partial of xs is f alpha s. That's the quantity that we say is a function of state that you have to postulate by constitutive assumption. We said it in 2010 with only our understanding was that we should do it in growth mechanics. And, some people would say, well, what's the difference? You're, splitting your deformation gradient in the current configuration into the product of two deformation. Isn't that the exact same thing as the growth tensor? The answer is no. This is a function of state. It doesn't appear as a state variable. So when I do the chain rule of differentiation that I showed you from Coleman and Gerton in like slide number 3, I would not include f alpha s. You see, it's a subtle difference, but what I want to say is the theory of internal variables is perfectly valid. I'm not trying to invalidate it. I'm trying to propose an alternative approach. And so it's great that there are analogies. It's not to be, one shouldn't be surprised that there are analogies, but the subtleties, the subtle differences is what makes this theory different from the common theory. So what example can I give you? So when the new generation is formed, then you could say, oh, for example, the new collagen that's deposited at the current time t is deposited in a stress-free state, even though the yellow collagen is already stressed. So how do you then formulate this mapping? The mapping says f alpha s is actually the deformation gradient of the master configuration at the time that generation alpha is produced. If you do that, that means that the deformation gradient of generation alpha at the current time alpha is the identity tensor. So obviously, it cannot carry. The strain will be 0, the stress will be 0. You understand? That's just an example. In Humphrey's work, they talk about deposition stretch. They think that maybe the collagen is a little bit stretched, maybe due to molecular forces, electrostatic forces. So this is what I mean by you propose a constitutive model. You cannot observe it. Once you propose it, then you can say, oh, okay, then I can use the deformation gradient in the current configuration to figure out the mapping. But that's only possible once you have adopted the constitutive relation. Okay, so now back to the thesis. I'm not going to go point by point. Hopefully you understand better what I meant by the reference configuration of the product of a reaction is a function of state. So now let's do a little bit more. I'm going to check my clock. Okay, so I'm going to try to be quick and not bore you with too many equations. Let me give you examples of reactive processes in solids which are not growth mechanics. Damage mechanics is a reaction. You can think of it as those molecules that start out with intact bonds. Upon loading and exceeding a certain threshold of loading, will produce molecules with broken bonds. This reaction is one way. The broken bonds will not heal, and so once they're broken, they're permanently broken, and they cannot store strain energy. So then the formulation of the deformation gradient is the same. But that's not this, we can apply the same idea to viscoelasticity. We can say that, there are two types of bonds in viscoelasticity. Weak bonds, for example, they could be electrostatic bonds, they could be hydrogen bonds. You can think of any number of chemical species of bonds that would apply, but they would not be covalent bonds. Those would be strong bonds. So in elasticity, if there's no damage, you assume that strong bonds remain intact. So that gives you the elastic response. But you have weak bonds, which are, you have polymers, long macromolecules, maybe local attraction of electrostatic forces. They break, but then they reform somewhere else, So what you do is you say that upon loading, they break, but then they reform, but they reform in a stress-free state, in which case you can use the same constitutive relation. So viscoelasticity can be described this way. By the way, that is how Tobolsky described the molecular mechanism of viscoelasticity, but he didn't use mixture theory to describe it. Plasticity, you could say, is very similar, except that when the bonds are reformed, they're reformed in a stress state. And so it's a more complicated formulation. Again, this is the paper that, a separate paper that Brandon and I have written which is currently in review. The reviews is taking a long time, where we describe plasticity using this framework. And so in thermal elasticity, you could say that the material U at time U becomes a different material at time V. Why? Because the thermal expansion changes its reference configuration. Maybe the change in temperature also changes its properties. But as long as you don't allow phase transformations, by the way, is another type of reaction, but I didn't include it here because, you know, going from solid to liquid, from liquid to vapor can also be described by this, but then my presentation would take 3 days instead of hopefully 45 minutes. Okay, so we have, I'm gonna go quickly at this point because I'm sure you have plenty of questions, but the only difference here is I'm no longer gonna assume isothermal conditions, which is the conditions that we use for biological tissues and for thermoelasticity, I mean for viscoelasticity and damage mechanics. So we're gonna allow the temperature to change. We're gonna now include the temperature gradient G, even the rate of deformation tensor and the composition in our list of state variables. You know, we have a mixture stress, a mixture internal energy, and so on. You can watch these slides in the video if you want, but the important thing is our evolution equation is the axiom of mass conservation. This is our free energy as a function of all the state variables. This is the chain rule. We're going to replace the kinematic relation here as usual, but also here we're going to replace this with the axiom of mass balance. So it turns out that this is not a state variable after all, or the time rate of change of a state variable. It is a function of state. So this term becomes different. You substitute these two sets of equations into the entropy inequality. You group the terms. As usual, you're going to conclude that eta is negative partial of C partial of theta. And you're going to conclude actually in this case that for arbitrary variations in D dot and G dot, you're going to actually find, and I'm going to show this, not only do you get eta as this, but the free energy cannot depend on the rate of deformation, nor can it depend on the temperature gradient. You are now left with a residual dissipation statement. So this term was 0, this was 0, this was 0, but this term is not 0. So we take this whole stress term and we rename it tau. And we leave it in our residual dissipation state. Now the, you know, since G is a state variable, the gradient of temperature is a state variable, the heat flux could depend on that. So you keep that in and you have this reactions. The reactions is the important part. We simply recognize that the rate of change of free energy with composition is normally called the chemical potential. Okay, so this is the residual dissipation statement. It is very important. It describes all the irreversible processes that you have in thermodynamics. We can give these names. I put them in purple because these are not standard names. You can explain all these terms. And if there are no reactions, you recover what Coleman and Knoll had, which is this residual dissipation statement. Since tau and Q both depend on D and G, you cannot extract one simple constraint for tau or for Q. But remember, the second law simply places constraints on constitutive relations you proposed. These are proposed based on experimental observations. So you don't necessarily have to find the most general constraint. You just need to make sure you don't violate the second law. So therefore, it's very common, it's not very common, it's the only way to do this in the classical literature is to use sufficient but not necessary conditions that this term is positive and this whole term is positive, which means Q dot G is negative. When you do that, you recover Fourier's law of heat conduction with thermal conductivity tensor, and the second law says it should be symmetric and positive semi-definite. And you find that tau must be a function of D, which means it's a viscous stress. I don't want to do the whole theory of viscous stresses, but for example, if it's a Newtonian fluid, it's a linear function of D, and this is the most general linear function for an isotropic material. And so the second law then says, if you plug this in here, that the shear viscosity and the bulk viscosity should be positive. So that's the constraint that the second law says. There's no such thing as negative viscosity. Okay, so now the residual dissipation statement, however, more generally contains this additional term from the reactions. So you can look up textbooks on reactive kinetics. It turns out that this mass supply term is related to the stoichiometry of your reaction. So if you know the stoichiometric coefficients of your reaction, you can get the net stoichiometric coefficient if you know the molar mass of each of the species. Let's say you have H2O hydrolyzes in 2H plus O. So H2O has a stoichiometric coefficient of 1 as a reactant and 0 as a product. H has a stoichiometric coefficient of 2 as a product, 0 as a reactant, and O has a stoichiometric coefficient of 1 as a product, 0 as a reactant. Then you find that only one function of state is needed for each reaction, which is called the molar production. So now your reactive power density can be rewritten as the product of the molar production rate with this quantity here, where now we express the chemical potential per mole instead of the chemical potential per mass. That's the more traditional way to express the chemical potential. So if you load the material and there is a reaction, you can say, I don't need to add heat. So that means that loading is enough to break the bonds. That's called a spontaneous forward reaction. This is what it's called in classical chemistry, is a reaction that can proceed forward spontaneously without the addition of heat. We call this an exergonic reaction, and this quantity must be negative for an exergonic reaction. However, if this quantity is not negative, you can still add heat in order to satisfy the second law. So you can drive reactions forward, not just loading reactions. You can heal a material that has already been damaged by adding heat and rebonding broken bonds, for example. These are just simple examples. So now you take these constant models, you plug them back into your energy balance. I'm going to skip the details. By the time you're done, you end up with the heat equation. This is what we usually call the heat equation. And CV that you see here is the isochoric specific heat capacity. By definition, it's the rate of change of internal energy with temperature. What causes the temperature to change? The dissipation due to the viscosity of your fluid. You stir your tea with a spoon, you remove the spoon, eventually the tea stops rotating. Why? Because you've dissipated the kinetic energy with this term, the viscosity. You also can change the temperature if your heat is converging, your heat flux is converging, you're going to raise the temperature. You are going to generate, change the temperature if you have Joule heating or microwave heating. And then now this term, which actually comes from substituting all of these equations in here, this is called the reactive heat supply density. That's the term I'm giving it. And it's related to the molar production rate and the chemical potential. This allows you to calculate the heat generated by a reaction. So if R hat is positive, you get an exothermic reaction. If it's negative, you get endothermic. So these are familiar concepts from thermodynamics. I just want to tell you, I have not seen any thermo textbook or any thermo paper actually give you a formula like this for the heat that's generated. So if you look up the classical thermodynamics literature, you hear about energy of formation and heat of reaction. So I want to just explain. So we describe the reactive power density as the product of the molar production rate with this quantity. This quantity is in fact the energy of formation. I call it energy of formation because it's a generalization of what is classically called Gibbs energy of formation in classical chemistry. But Gibbs energy of formation is formulated when you assume that your state variable is pressure and you're analyzing processes at constant pressure. I'm using deformation, which means volume, as my state variable, and this expression is valid for any process, whether constant volume, constant temperature, constant pressure, or not. It's valid, so I don't call it Gibbs, I just call it energy of formation. The reactive heat supply density, similarly, is the product of the molar production rate with this quantity, which I simply call R bar. And I chose to call it heat of reaction, but you need to understand that it's often called enthalpy of reaction or enthalpy of formation in the classical literature. Why? Because they lump this term, which was in the energy balance. Allow me to go back for a second to the heat equation. They lump this term here with double dotted D with this term, and then they call it the enthalpy of formation. So I don't lump it. It doesn't come out naturally in my formulation, in our formulation with Brandon. So I simply choose to call it the heat of reaction instead of the enthalpy of reaction. So in summary, I'm proposing that we can use reactive mixtures to model all dissipative processes in solid mechanics. We can estimate the heat that's generated by the dissipative process where you convert free energy into heat. You can also track the evolution of the composition, which will show an evolution in the free energy and therefore in the stress, so you can get viscoelasticity, plasticity. And if you're wondering, how do we reconcile this with the work of Truesdell and Toupin about the history of the deformation, the answer is you capture it with this constitutive model. So they had all the ingredients, Truzel and Tupin and Coleman and all had all the ingredients, but they just didn't put them together like we did here because perhaps they were not exposed to growth mechanics. And that's really what I wanted to say. All of this framework was driven by our observation that, you know, for growth mechanics to describe our own experiments, we needed to revisit classical concepts, and we realized that the theoreticians of the 1960s simply were not aware of growth mechanics as an option. And so now that we know that, we have more opportunities to expand the theory. This is Brandon. He's the person who's mentioned in all these papers. This is Bob Nims, who ran the models and the experiments for cartilage tissue growth. And our work is supported by the National Institutes of Health in the United States. Thank you.